Namaskar my dear friends. Let's talk about intelligent power module, which are also called as IPMs. Okay, and what are the importance of IPM in design and techniques and their details. We can see some of the examples also for various applications is like motor drivers. So first of all, you can see we have IPMs which are integrating a lot of other parts, like whether it is a IGBT or gate driver, or we have sometimes it is having shutdown facilities, or we have basically temperature sensor device or so many other things, and as well as our three-phase motor driver. So basically, why do we go ahead with IPM? So first of all, we'll try to understand what are the different application or different areas that we try to utilize IPMs. Okay, so as you can see, for most of the applications we have let us say electric traction control is there, like we have main inverter, so there we utilize IPMs. We are utilizing onboard chargers. Then we have DC-DC inverters for electric vehicle or heavy electric vehicles. We have HVAC and climate control. HVAC is basically nothing but we have like heating systems in our homes or ventilation systems in our home. We have air conditioners. So all these things require some motor to like for the air to flow, or basically air to flow in and out, something like that. So for air control, basically we utilize some motors, some kind of motors, and to make them like run properly, we try to utilize IPMs. Okay, we have EV charging, DC fast charging stations. We have energy generation and distribution like solar power or something like that. We have industrial motor control. We have power supplies and converters where we utilize our IPMs. We have home and professional appliances, like we have fridge, washing machines, dishwashers. So many things are there that we where we try to utilize IPMs. So if you see a list of them, you can see very quickly. Let us talk about home and professional appliances. So there you will be finding air conditioners for like window, wall portable or something like that. We have dishwashers are very useful these days, and we have to find a way to find out very compact design and very low cost design. We have dryers, we have induction stoves, we have kitchen hoods, we have refrigerators, freezers, washing machines. Okay, so just name a place where there is a motor. You will be needing something which is called IPM to design your board. Okay, coming back to industrial tools and motor drives and equipments, we have AC motor drives, we have servo motor drives, we have PMSM or BLDC motors, we have motor control fans. So basically industrial fans are there. We have pumps and compressors. Okay, coming back to home and building city automation, so basically you have commercial indoor outdoor HVAC units. HVAC unit is nothing but uh, like we have heating, ventilation and air conditioning units. We have central indoor outdoor HVAC units. So basically in commercial building you will be having lot of requirement of ACs, right? Coming back to the factory automation, so we have robot arms, a lot of robots are there, so they utilize industrial robots or something like that. We have automotive motor control, where we will be trying to use automotive BLDC motor control or something like that. And similarly these days body and convenience also are getting used. For that we will be needing this kind of IPMs. Okay, so these two images were actually taken from STMicroelectronics website, where they had listed out all these applications very precisely. So thanks to them. Coming back to the one of the page that they have mentioned very clearly, like how discrete approach works for this particular design, and how our intelligent power module all in one approach will be there for the solution, right? So as you can see, we require a lot of like passive components like diodes, resistors, capacitors. Then we need like high voltage gate drivers, and we need IGBTs as well as with forward wheeling diode, like uh, freewheeling diode, something like that. So this is going to take a lot of space and lot of like time to design all these different parameters components, right? So as you can see, we have high component count will be there. we have larger PCB design, we may end up having significant stray inductances or something like that, and it will be very difficult to mount our heatsink as well. Okay, now let's get into the IPM phase. So in IPM, what is happening is all these components in one. Okay, and so this is this you can see like all in one component. We have improved design time and reliability. We have reduced manufacturing effort as well, like manufacturing cost will be little lesser because we don't have to assemble lot of components, and we have minimized stray inductances, and also we have easy heat sink mounting so that you can dissipate your heat or flow your heat properly. So what we'll do is we'll try to take one example from STM IPM so that we can understand what is IPM, what are the different parameters that to be taken into account, and before that what we'll do is we'll just have a quick look of a STM portfolio, okay, like STMicroelectronics portfolio. So we have slim nano series, we have slim second series, and we have slim high power series. Okay, so as you can see, a slim nano series can be utilized for our fan application, or we have lot of other application like fridge, washing machines, or strollers or something like that is there. Okay, similar to that we have slim second series of with higher power rating, and we have slim high power rating can be used for your industrial robots and all these air conditioning units or something like that in industries. Okay, so why don't we do one thing? We'll try to understand a basic fundamental block diagram with IPM system. So let me just open it for you. And what happens very simple is, let us say we have a DC input voltage which is going to be, let us say 300 volt to let's say around 600 volt that will be needed to supply to the IPM. Okay, so that will be my input, positive input and negative input from this. So basically it comes from your we have AC, and AC will be going to the bridge rectifier. Okay, bridge rectifier. So this bridge rectifier will be giving you this DC input high voltage, and that will be getting connected to the IPM with some bulk capacitor. So that's the main understanding of putting it to the voltage. Okay, so so this is how it works. Next is a lot of other parameters are also taken into account. I'm not showing it to you. Like let's say we have directly high voltage batteries in our EVs these days, so we just need some safety features here, like we will be needing a lot of like fuse, then moving like MOVs or thyristors. We will be needing some common mode chokes, okay, CMCs. Then we will be needing some capacitors like X capacitor, Y capacitor. Then we will be needing some like TVS diode as well. So these are the safeties and filters that we will be utilizing after my DC, and then only we will send it to my IPM. That is by default, that will be a part of our circuit design concepts that we will see. Then we can have one AC to DC converter as well. Okay, so if we take AC DC converter, which can give me like a 15 volt output, and let's say from here I can generate with a regulator to 5 volt output. Okay, so this VCC and VDD, which will be like 15 volt and 5 volt, can be utilized. So 15 volt will be utilized for power supply to the IPM for other functionalities, and this 5 volt or 3.3 volt also can be used for our MCU application, like my digital controller, right? So this is my controller. So this controller side will be taking a power from, let's say, 5 volt or 3.3 volt, whatever the logic level that you want to use. Okay, 5 volt or 3.3 volt. Coming back to the other part, so this IPM will be having all the three phase output, which will be having U, V, W, and this will be going to drive the motor, and there only we will be having option of having the shunt resistors. Either this can be three shunt resistor for each of the phases separately, and they can be going to the amplifier like current sense amplifier or something like that, and it can be sent to the MCU for detection. At the same time, they can be used lot of like comparators or something like that for other functionalities. I have not connected here. You can have comparator for your temperature sensor or other features like shutdown features. So those controls also can be sent to the microcontroller for taking a decision. So this will be my controls. Coming back to the high side and low side motor drives, we will be needing 6 signal, okay, so which will be like high side and like low side. So so high side and low side 3 PWM and low side 3 PWM will be coming from microcontroller to IPM, which will be helping to drive the motor properly. So this is a very like fundamental block diagram for system based on IPMs. So now what we'll do is we'll try to understand IPM in deep method. Okay. We have now good knowledge about what is IPM and what are the different uses for IPM, how a different like a basic fundamental block diagram of IPM system looks like. So we'll just proceed to one of the data sheet and we will try to understand the design and details of this particular IPM system. Okay. So basically these IPM intelligent power modules, I have taken very basic one, which is STGIK STGIK50CH65T. Okay, so this is a slim high power IPM which is having 3-phase inverter with 50 M capacity, 50 amperes capacity, and 650 volt short circuit rugged IGBTs. Okay. So as I have been telling you earlier itself, like very first thing that we have to always read about a data sheet is what are the features that this particular component is presenting to us. So as you can see, we have IPM of 650 volt with 50 amperes of rating, 3-phase inverter, bridge including control ICs for gate driving. Okay, so gate driver control ICs are inbuilt inside the IPM itself. Okay, we don't need a gate driver separately. We have a 3.3 volt and 5 volt both TTL and CMOS inputs with hysteresis. Okay, so we have a compatibility of 5 volt and 3.3 volt logic labels. We have under voltage lockout for gate driver as well, like it can be designed with a minimum voltage. Otherwise like what happens is suddenly the system should not work, so it should reach some place and then only it should go to work. Okay, so this is how we can design our under voltage lockouts. We have built-in Bootstrap diodes, so we don't need external diodes for Bootstrap functionalities. We have a short circuit protection, we have shutdown pin and fault output as well, like if there is a temperature increase beyond the threshold level, then you can the IPM will get shut down based on the threshold limit that is there, or if there is any fault, it can help us to indicate based on the high or low what is the fault, right? Then we have separate open emitter outputs, we have comparator for fault protection. Okay, so it will be it will be comparing with a comparator output, and this is how it will be saying us what is the faults. We have short circuit rugged, we have very fast short recovery diode. Okay, so we have a very fast soft recovery diode. Now we will be going to talk about fully isolated package. Okay, coming back to the isolation rating, so isolation rating is actually 25 volt RMS. Okay, so and we have 100 kilo ohm NTC for temperature monitoring, so we have inbuilt NTC as well, so which we will be not needing from outside to see the what is the temperature at the junction. And at the same time it has been recognized by UL 1557, and as well as the file number is this one, which is E1 E81734. If you talk about this particular slim high power IPM, what is the specific usage of this particular ones is it can be used in HVAC system, that is heating, ventilation and air conditioning systems. It can be used in GPIs, it can be used in servo motors and pumps and compressors. So these are the different applications that can be utilized, and it has been like recommended by the manufacturers. Coming back to the description, so as you can see, this is new IPM intelligent power module is a part of high power slim. So slim is a trademark, or like it has been a word used by STM only, so it is a patented word, and the full form of this slim is a small low loss intelligent molded module. Okay, so this is a family that provides a compact high performance AC motor drive. Okay, in a simple rugged design. Okay, good. So let's get into the next manner. So what is the schematic and pin description that we'll be talking about? Okay, so basically you will see we have high side IC, so three high side will be required controller, so 1, 2 and 3. Similar to that, three low side will be there, so low side controller is there also, 3 will be there. Okay, like you can see we have H in U, V and W. So high input U, high input V, high input W. Okay, similar to that we have low input U, V and W. Okay, we have a high voltage logic supply for U and V and W phase as well. Okay, so these are like high voltage logic supply as well, which will be taking around 15 volts of value. Then we have output U, output V and output W. We have bootstrap capacitors for U, V and W phase. Okay, so these are the like 6 parameters that we have got. We have no connection pin 1, which is pin number 13. We have temperature pin. Then we have coming back to the fault output, we have CFO scene that we will talk about what are these pins. Okay, and we have VCC low. So VCC high was there and VCC low logic supply is also there with this particular pin. Okay, coming back to the other sections, so we have inbuilt like 3 phase IGBTs. So these upper ones are high side and lower one are like low side drivers. Okay, with you can see we have freewheeling diode inbuilt inside this, so we will not be needing any separate protection for that purpose. And we have inbuilt NTC, which will be helping us to give us the temperature of the particular like ICs. Coming back to the main supply of this IGBT, so that will be coming from P, which will be taking, let us say, 300 volt or 400 volt which will be coming from a high voltage DC supply, which will be having let's say car batteries or something like that, or which we have like UPS batteries or something like that. Otherwise, if there will be AC source, so then AC2 we will bridge rectify it and then send it to the input of IGBT. Now coming back to the motor, so this is going to get connected to the motor, which will be UVW phase. Okay, and at the same time they will be taking the shunt resistor input through like NU, NV and NW. That we will see what what are NU, NV and NW. So let me give you a brief introduction about the pin functionalities and pin like description. So as we come down here, all the pin names and their description is given. So we have out U, as I told you, like it is high side reference output for U phase. Similar to that, it has boot U, so that is bootstrap voltage for U phase. We have VCC HU, that is high side voltage power supply for U phase. And we have H in U, that is going to be high side logic input for U phase. And we have out V. So similar to that, out U, boot U, VCC HU and H in U, right? We have for HV, and then similar to that we have HW. Okay, so that is for high side U phase, V phase and W phase. We have all the pins. Okay, coming back to the temperature sensor output, so that is NTC thermistor output with T pin, pin number 14. Then we have low side logic input for U phase, V phase and W phase, as I mentioned already in the block diagram. Then we have shutdown pin, that is fault output pin. Then we have capacitor for fault output setting. So if you want to set some value, then we can utilize this particular capacitor, that we'll see during the circuit design concepts. We have comparator input, that is C in. We have ground pin with GND. Then we have low side voltage power supply, which is VCCL. Okay, so as you can see, we have VCC HW, HV. Similar to that, we have just only one VCCL, that is more than enough. Okay, coming back to this NW, NV and NU, so like NU, NV, NW, which I was talking about here, this one. Okay, so these three pins are going to be used as, I'll just tell you here, we have negative DC input for W phase, V phase and U phase. So basically what happens is, this is the motor that is there and that is going to get connected with U, V and W, and they will get connected through the shunt resistors, and this is how this will get connected to NU, and then this will get connected to NV, and this will get connected to NW. Okay, so this is how it will be working up, something like that. Good. So we are good to go ahead with the pins. Now we'll talk about W, V, and U. So that is phase outputs for the motor driving, and then this is my positive input, which is high voltage, and this is NC pin, which is not connected. So there are various other manufacturers as well, like if you talk about various other manufacturers for IPM, what we can do is, let me just write it here for you. So IPM that generally we try to utilize is, like, let us say from Mitsubishi, then we have STMicroelectronics, which we are seeing a data sheet right now. We have onsemi, we have Fuji Electric, okay, Fuji Electric. So we have several designs with Mitsubishi, which is there in abundantly available in India as well. So what we'll do is, we'll just proceed with the datasheet first, otherwise we'll miss out some of the concepts. So let us talk about absolute maximum rating of this particular IC which we are seeing. So you will see that VPN, that is the high voltage input for between positive voltage, and NU, NV, and NW is 500 volt. So 500 volt is the maximum voltage that you can apply, and surge voltage can reach to 550 volt. We have collector emitter voltage for each IGBT, so that will be reaching up to 650 volt. Okay, so the IGBT rating has 650 volt. We will talk about continuous current for each IGBT, that is going to take up to 50 amperes. We have peak collector current for each IGBT for less than 1 millisecond will be reaching to up to 100 amperes. Okay, so basically continuous current is up to 50 amperes only, but it won't fail if there is a high peak current for less than 1 millisecond for up to 100 amperes. Okay, we have a total power dissipation at 25 degree centigrade for each IGBT is 150 watts. Okay, so as you can understand that 500 volt multiplied by the current 50 is going to be 150 watts for each IGBTs. Okay, now we have a self protection supply voltage limit. So it has a self protection from 13.5 volt to 16.5 volt. So that's the reason we are going to supply 15 volt. Okay, so VPN will be VPN will be having 400 volt. Okay, now coming back to the control parts. So there are two parts. One is IPM part, which is having the IGBT parts, which are basically nothing but called as inverter parts. Okay, like from DC to AC, like 3 phase, which is U, V, and W phases. Okay, for control parts, we will be having supply voltage of VCC, which is going to be maximum 25 volt, which will not damage the IC pins. We have bootstrap voltage, which is also 25 volt. We have V output pin applied between outx and ground, that will be 650 volt. We have comparator logic voltage, and all other pins are there. So similar to that, you can see these are the voltages that is available for our absolute maximum rating, but these are not recommended. We have a recommended values for each of them that we will be seeing into. We have bootstrap diode, which is having a capability of 650 volt. Now let us talk about as a total system, like what is the functionality. So we have voltage isolation of 2500 volt RMS, that is 2.5 kV. Okay, 2.5 kV. We have junction temperature that will reach up to maximum 175 degree centigrade, and driver IC and bootstrap diode operating temperature junction will be up to 150 degree centigrade. Good. We have module case operating temperature range, which is up to 125 degree centigrade. So that's the understanding. Now we have thermal data. So thermal data is very good here. You can see thermal resistance junction to case on a single IGBT will be 1 degree centigrade per watt. For 1 watt of power dissipation, just 1 degree centigrade temperature rise will be there. and junction to case single diode, that will be having 2 degree centigrade. So for IGBT it is 1 degree, and for diode it is 2 degree inside the IPM. Now let's talk about electrical characteristics. So the one that we just now discussed was absolute maximum rating, which is not recommended. However, we have to have those parameters in mind so that our IC pins doesn't violate that those limits at any cost. Similar to that, we will talk about electrical characteristics for inverter parts. So in inverter parts, as you can see, we have a collector cutoff current which is going to be 25 microamperes. Okay, at this particular voltages, like 650 volt of VCE, and VCC or V boot voltage will be 15 volt. So all the test conditions are for VCC as 15 volt, input supply as 5 volt, and we have VCE as 650 volt. So we have meter saturation voltage is going to be 1.8 volt. Okay, so this was the collector and emitter. So let's say this is my emitter, this is my collector, and this is my gate. Okay, so the voltage between these two must be in saturation voltage, it is 1.8 volt to 2.3 volt. So this is the understanding that we should have. Coming back to the diode forward voltage, so diode forward voltage is 2 volt. Okay, or it can reach to 2.25 volt for other junction temperature. Let's talk about inductive load, switching time and energy. So that was inverter parts. Coming back to the switching time and energy. So on time, off time, all these things are given here. So these are in nanoseconds. So that's not to take into too much account right now. We'll talk about these things during our design and writing the code for that. So we have load switching time and energy consumption in high side and in low side. Now if you want to test your switching test circuit, so this is nothing but like they have given only one like high side one switch they have taken, low side also one switch they have taken, they have given some inductive load and with this particular supply voltage supply. So we'll be talking about these things later. Instead of this, what we will do is this is for IC that has been recommended us to test how to test this particular IPM. Okay, so they have showed it for only one of the high side, let's say U phase, V phase, or W phase, something like that. Coming back to the other part, which is my control parts or protection parts, so that is also not to worry about. Let's get into the, yes, we have this one, fault signal output and shutdown signal input. As you can see, we have fault output pin shutdown release voltage will be 2 volt, and we have threshold voltage is 1.5 volt. Okay, and going to back to hysteresis, so hysteresis is 0.5 volt. That's the reason for 2 volt it is reaching 1.5. We have fault pin output voltage in normal operation. So if you have normal operation, this will be 5 volt. Okay, and when there is a fault, then it will reduce to, or it will go to 0. Okay, so that's the understanding. So if there is a voltage at fault output pin during error signal, so that time it will go to 0 logic. So when there is no fault no, then it will be high, and if there is a fault yes, then it will be going low. Okay, so this is how the fault signal will be there. Let's talk about the protections. As you can see, we have C input overcurrent protection detection, that is 0.5 volt. So there was C in pin which will act as a comparator. Okay, so that will be giving us an understanding of what is the protection feature that we have to take into account. So let us say C in pin input current is also there, which is just 2.5 microampere. Now we'll talk about some of the characteristics that is there. So total bootstrap current versus FSW, that is switching frequency. So switching frequency, you can see as my switching frequency is increasing, so up to around 16 kilohertz, so this is going to reach to 20 kilohertz maximum. So you can see my bootstrap current is increasing slowly. Okay, now talking about TFO and CFO characteristics. So CFO is there, which is in microfarad, and TFO is in milliseconds. So this also increases with increase in CFO. That was actually fault output. So time of fault output, time of the kind of response to the fault output will be going with 100 millisecond, and this is uh, CCFO, that is your capacitor at the fault output. So if capacitor at the fault output increases, my time response for fault output also increases. Good. So this is nothing but just a C input test circuit and timeline. Now we'll talk about Bootstrap diode. So this is their like Bootstrap diode characteristics. What they have told is within what is the forward current and what is the forward voltage. So based on forward voltage, my forward current is increasing, as you can see. So generally we always talk about voltage versus current, and it actually works like this. So the same graph is actually shown here, but it is in opposite manner. You can see as my voltage is increasing, suddenly there is a knee voltage or cutoff voltage, and from there sudden my forward current is increasing. So as you can see, we have lower junction temperature, my current is higher, or it has a more voltage drop capacity, like forward drop, cutoff forward drop. But with increase in temperature, we are having lower cutoff voltage. Okay, so forward cutoff voltage is lower for the Bootstrap diode that is there. Let's talk about NTC thermistor. So NTC thermistor is having resistance at 25 degree centigrade to be 100 kilo ohm, and resistance like beta value, that B constant, between 25 to 80 degree centigrade it is having 4395 Kelvin. Okay, and we have operating temperature range from minus 40 degree centigrade to 175 degree centigrade for this NTC thermistor. So if you talk about the characteristics of NTC thermistor, so as you can see, we have lower temperature, the NTC value is quite high, and as temperature increases, my NTC resistance decreases slowly. Okay, so you can see that. So at 25 degree centigrade it has 100 kilo ohm. Sorry, what was the value? Yes, it has 100 kilo ohm resistance, and similar to that, for higher temperature the value will be reducing, and this will be monitored through some ADC after amplification and filter will be trying to take. If you take a zoomed value, so from 75 degree centigrade to 100 and 30 degree centigrade they have showed it, 5 plus 10 15 20, 25 125 degree centigrade they have shown it. So you can see the variation is from 10 or a 15 kilo ohm to going to be 2 kilo ohm. So this is the complete variation for your NTC resistance versus temperature. Coming back to the application circuit diagram, so this is what we need to understand, how to understand this particular let me load it. Okay, so as I told you in the block diagram of the IPM based system, so what happens is basically, let us say we have a microcontroller. Okay, so in this microcontroller we will be having PWM signal, let's say U, V and W phase for high side, and then U, V, W phase for low side. So this is how they will be going to the gate driver of high side and low side gate drivers for the driving of IGBTs. So this is the very basic understanding of my high side driving and low side driving PWM signals. They are going through one RC filter. So as you can see, one RC filter is there which is used as R1 and C1 from the microcontroller. So they are not directly taken into it. We will be showing it to you what is the very rugged design or something like that. We will be taking up isolators, we will be taking buffers, then only we will be sending it to the IPM pins, which is HU. Okay, similar to that other pins as now. Let's talk about the motor driver. So motor driver, as you can see, we have connected a U phase, V phase and W phase directly to the motor, which is being monitored or which is being driven. Coming back to the bus voltage, so bus voltage is like high voltage pin. So we have the high voltage here, battery or maybe driven from the AC source, and then it has been rectified to a DC source. So this is my DC signal of high voltage. We will be requiring a DC link capacitor, that is like a high value capacitor, let us say 100 microfarad, or some 1000 microfarad, based on the need that we'll be needing. Okay, for very small application you can use a small capacity. For very high voltage applications we will be needing as high as like 1000 microfarad, or even it goes to millifarad as well. Good. Coming back to the other part, so this U phase, V phase and W phase, they are taken into account as a output for W phase, U phase and V phase. So this is acting like a loop back, and basically it is going to have a closed loop control system. Okay, so this is how you will be recognizing it. Coming back to the shunt resistor, like what is the current regulation in our current being consumed in each of the phases. So for that we have NU, NV and W, and there is a place where we try to connect some shunt resistor. So this is my current sense resistor, and this current sense resistor is going to go through a filter which is RCF and CCF, and then it is going to go ahead into your scene comparator input. So this scene comparator input is going to get into here. There are other design methodology as well, like this current sense resistor output can be taken up to like a op amp or my MCU, and this can be taken into an ADC after this amplification, so that we can understand what is the current that is flowing through each of the lines. So basically sometimes what we do generally is, for each of the lines we will be using a separate shunt resistor, so that we can closely monitor the current consumption in each of the IGBTs. And sometimes to reduce the cost of the system, we try to utilize a single shunt resistor for all the three of line together, and that's how we will be reducing the cost of design. Okay, so I think you have now a very good idea about this complete circuit design of IPM based system. So let me just clean it up a little. Okay, now what are the pins that is still remaining? We have NTC pins, that was temperature pin, that is taken into account for my ADC, and which will be monitoring what is the value of temperature based on the NTC variation, like NTC resistance variation. We have fault output in that has been pulled up, and this pull up will be taken into my MCU controller again, and this is how we will be recognizing whether this is in fault condition or this is in safe mode, that it is in normal operation mode. So good. Hope you have a very good understanding about this particular block diagram, or like this particular application circuit that has been given in the datasheet itself. So as we have understood the general application circuit, which is very minimal, like we will be giving you the application circuit for one of the air conditioner design, that will be easy for you, or motor driver design for water pumps, that will be easy for you to understand how IPM actually works. But however, we will move to the general guidelines that is given by the datasheet itself. So we have external connection between pin output U, V and W are required. Okay, that is there. So just now I explained you this particular circuit, right? So in that you can see out U there is external like C boot capacitor or DZ or C1, C2, C3, something like that is there. So those are needed. So that's the understanding they are going to give you here. So right now it is not needed. We'll be moving to the next page. So the complete circuit has been explained here. If you want to understand the complete circuit by yourself, read this particular page number 14, and this guideline will help you to understand each and every parameters of this particular components, how they are used, R1, C1, and what is their functionality, something like that. Anyway, I have explained you that's why these filters are needed, how we will be if we are going to design, we will be introducing buffers, we will be also utilizing somewhere like optocouplers for isolated design. Okay, so isolated design is there, then non-isolated designs are there, so lot of different concepts are utilized in IPM systems that we will try to understand. Now let us talk about a recommending operating condition that will be used for this particular IC that we are discussing right now, which is going to be supply voltage is recommended to be 300 volt or maximum 400 volt. Okay, so that's the understanding we should have. If there is a voltage high or voltage rise at the input supply, then you have to make sure that it reduces to 300 volt. We have control voltage supply for your logics, which is going to be 15 volt, like low side and high side both. Okay, then we have high side bias voltage, so bias voltage again 15 volt. Okay, so that will be for U, V and W phase using the bootstrap pin. Okay, we will talk about blanking time to prevent arm short or something like that. This is also called as dead time, so minimum it should be 1.5 microsecond. And we have frequency of PWM input signal, that is for all the three high side and low side supply will be there. Okay, just now I told it to you, let me just show it to you quickly. We have, see, H in V, H in W and H in U. So high side U, V and W. Coming back to same way, low side U, V, W. So those are all signal coming from the microcontroller PWMs. Okay, 1 2 3 and these three. So these will be the PWMs that we'll be using, and frequency will be, which will be shown by here, which is going to be maximum 20 kilohertz. So you cannot use a PWM signal more than 20 kilohertz to drive the high side and low side IGBTs. The case temperature must be less than 125 degrees centigrade, otherwise there will be a shutdown of due to thermal heating. Let's talk about typical characteristics again. A little bit of typical characteristics given, like output characteristics. So if you see what is the voltage between C, that just now I told you, this was my collector and this was my emitter. So the voltage between VCE increases with increase in the current, right? So as my current increases through the IGBT, my VCE also increases, and for a supply voltage of 15 volt it is shown. For other voltages there may be a little bit shift, but you can see voltage maximum is reaching at 50 ampere of current, it is reaching to be 1.8 volt. Okay, so if you are working with lower current, then it will be reduced. That's the understanding. If we talk about what is my saturation voltage versus collector current, so collector current is increasing and my saturation voltage is increasing accordingly. Okay, so as you can see, there is a little bit increment in the saturation voltage. So let us say we are working with 50 volts. So if we are working with 50 ampere, so in 50 ampere at 25 degree centigrade, my saturation voltage between VCE will be close to 1.8 volt. Just now we saw here as well, and the same way here is. So it is given. So this particular point, it is showing what is the saturation voltage between collector to emitter junction. Let's talk about IC versus case temperature. So what is the collector current? So collector current, as it increases, my temperature is there. So the safe operating area is this one. Like up to collector current of 50 amperes, you can work up to 25 degrees centigrade. As my temperature is increasing to, let us say, 75 degrees centigrade, your collector current must be reducing like this. Okay, it should reach to 45 amperes. Here it is 45 amperes. Then if you are still increasing the temperature of the system, let us say it reached 225 degrees centigrade, it may go for shutdown, or before that it will be working up to 25 degrees centigrade. So as you can see, the complete span of this particular IC to work continuously with any temperature range is 25 ampere. For diode forward voltage current, we have already seen, like what is the forward current and what is the forward voltage. So generally it may be little confusing for you guys to understand this, but anyway we have to manage with this. As my forward voltage is increasing, as you can see, the forward current is also increasing. So that's the diode characteristic. Generally we have studied voltage versus current in milliamperes it will be. So as it crosses, and then it starts increasing. So this is my, let's say, VF, which is cutoff voltage. Okay, so this is how it works. So same way it has been shown, after a particular point it is started increasing. So this was all about particular characteristics of this particular IC. There are other functional characteristics that's not required right now. Coming back to the package information. So if you talk about package information, it has total 30 number of pins. So let me just give you a proper understanding. Between pin number 1 to 22, we have little bit closer functionalities, like closer pitch, and between 23 to 30 we have bigger pitch. So this is actually going to get the like 400 volt inputs and all, and then they will be driving the U phase, V phase and W phase, and this will be the NU, NV and NW pins. So that's the understanding. That's the reason they need little bit higher pitch, so that we can have a proper heat dissipation and thermal capabilities. So alright guys, hope you have a good understanding about this, and as you can see, this particular IC has been released in 2021, and this is a very new IC for any of the application that we are looking for, and this is the contents that you can directly get into the IC. Let us say we want to have what is absolute maximum rating, you can directly jump there like this. So it is not going there, so yeah, it is going here. So page number 4 it reached. Similar to that, if you want to have some other like parameters, let's say NTSC thermistor or application circuit guidelines, so all these things are available, you can directly get into that. So in STMicroelectronics, basically the contents, table of contents is given in the last pages. In other manufacturers, they try to give in the first pages itself. So I understand now you have a very good idea about what is IPM and how IPMs are utilized in a system where we have lot of different applications that we saw just now. So our aim would be to give you a little bit more details about various other ICs first from different manufacturers, and then we'll try to understand how we can design a particular circuit for our exact application. Let us say my like motor drivers in automotives, or in solar panels, or we have home appliances like fridges, washing machines, we have motor controls like robots or something like that. So all those places we'll try to have one exact implementation that we have in our industries, that we have supported for our like various projects. So we'll be seeing those one by one. So if you do have any questions regarding the selection of IPM, or which IPM will be most suitable for your applications, what should be the power rating, what should be the current rating, and how based on the power my selection like gets changed, so those all things we'll try to understand one by one. As you can see, we have like IPM within SMD package also for very low power ratings. So because some of the places we don't need very high power capability, so that time you can utilize these SMD IPMs as well. So good. Please put down your queries and comment box, and give a thumbs up if you are liking the explanations, and if you require any specific information about any of the circuit design concepts, or any of the like requirement that is there at your projects. Please put down your thumbs up and like and subscribes. Thank you so much.